All right, let's go ahead and run this bad boy. So again, we're going to use GraphX to analyze the superhero social graph that we've used earlier in the course. And we're going to take examples of actually constructing a graph in GraphX using that social network of superheroes. And we're going to analyze that graph by finding the top connected people in the graph, and we're going to use Pregel to do breadth first search on the graph and find the degrees of connectedness between Spider-Man and everybody else in the graph all at once. Let's see how it works. So I've already imported the graphx.scala file from the course materials into my project here in the Scala IDE. Let's walk through it quickly again. We went through this in the slides earlier, but sometimes it just seems a little bit more real when you actually see it in an editor, doesn't it? So I've imported some stuff that we've imported before. I'm importing GraphX as well here, so all of the GraphX libraries are available to me. We talked about these functions that we're going to be using with FlatMap to create a vertex RDD and an edge RDD that together make up our graph. So let's start with the vertex RDD. What we're going to do is pass in the marvelnames.txt file into here, which is just a text file of superhero IDs and their names separated by white space, by quotes actually. So let's split that out. We will convert the ID to a long, which can then in turn be converted to a vertex ID for GraphX. Okay, so vertex ID is the same thing as a long, and then we'll just associate the name as the data associated with that vertex. Okay, so we're just going to go through it one line at a time, and if we see a valid superhero ID, we will return a vertex ID string tuple. Otherwise, we return none. Okay, because there are instances of invalid data in here. Like I said in the slides, turns out the superhero IDs over 6486 don't really exist, so we can just throw them all away. Now, creating the edge RDD isn't much harder. We just go through the actual marvelgraph.txt file where we have the actual connections, and again, the format of that is a given superhero ID followed by all the IDs of that superhero's connections. So all we do is we build up a list buffer of edges, where the edges are defined by integer vertex IDs, split up the input line, extract the superhero that we're talking about from the first field, and then create a new edge for every subsequent field between that superhero ID and that connection. So we build up this list of edges that we convert to an actual Scala list to FlatMap, and that gives us back a bunch of edge objects created from each line of input data from marvelgraph.txt. Putting it all together, we'll create our vertex RDD using parse names. We'll create our edge RDD using make edges, using all the code we just talked about. And then we'll make a graph out of it. So we construct a graph out of our vertex RDD, our edge RDD, pass it in a default case for edges that don't point to anything in particular, and we're going to cache that graph because we're going to use it more than once. So let's actually see if this code that we talked about in the slides actually works. First thing we're going to do, we're going to print out the top 10 most connected superheroes. Let's see what we get. So all we have to do there is call graph.degrees, and that will give us back an RDD of all the number of edge connections to every individual vertex. We'll join that with the vertex data itself so we can get back the actual names associated with each vertex. Otherwise, we'll just get a list of vertex IDs, and that's not very interesting. Sort it by the actual count of degrees connectedness. Take the top 10 and print them out. Okay. Next, we're going to do what we did before with the degrees of separation from Spider-Man, but this time we're actually going to do it for the entire graph all at once. So first thing we're going to do is say we're going to start with character ID 5306, who is Spider-Man. We're going to set up an initial state of our graph where we call map vertices to actually check whether you are Spider-Man or not. If you are Spider-Man, then your vertex attribute will be set to 0. Otherwise, your attribute, which represents the distance from Spider-Man, will be set to infinity initially. And now, here's where things get a little bit complicated with Pregel. So we're going to use the Pregel algorithm to actually iterate through the graph and measure the degrees of separation between each character from Spider-Man. So Pregel gets set up with, first of all, an initial message. So the initial state is going to be infinity distance coming into everything, and a maximum number of iterations of 10. So with that out of the way, we pass in 3 functions. The first function is our vertex program, and this is going to say that as a message is received, we're going to preserve the minimum distance between the incoming message and what we already have. Okay, so that just preserves the shortest distance as we iterate through. We have a function that will send messages to all the neighboring vertices. So in the case where we have an actual number in a node that we haven't explored yet or haven't traversed yet, we will send off a message to all of the neighbors with that distance plus 1. So this just propagates out the distance as we go from each superstep to each superstep. Otherwise, if this is a node that already has infinity in it, meaning that it hasn't been touched yet and is white in the parlance of our coloring terminology, will do nothing at this point. Finally, the reduce operation will preserve the minimum of the messages coming into a node if more than one is received. So if we're getting conflicting information about the distance at once, we'll preserve the shortest distance in that case as well. And that's all it takes. So with that, we can actually kick off Pregel. We're going to actually cache the final results of that operation. Okay, we're going to end up with a BFS object here that we can then play with. So we can just say bfs.vertices, and that will get back the end results of that Pregel traversal. And what we'll end up with is vertices that contain as values the actual degrees of separation from Spider-Man when we're done. All we have to do is join that with the vertices again, so we can just get the names back in there, and we can take the first 100 results, whatever they might be, and print them out. So we can sort of explore the data there and see if it's working. And finally, just to recreate the results of our earlier example in the course, we'll look specifically for the character Adam 3031 and make sure that we actually get a degrees of separation of 2 from Spider-Man, which is what we saw earlier. So let's go ahead and print this and kick this off. I already created a run configuration for this GraphX. Hit run, and you'll be surprised at how quickly it actually goes. All right, we've already constructed the graph, and we're done already. I mean, that's kind of impressive, actually. So let's take a look at what we got. All right, so we chugged away, we constructed our graph, and pretty quickly we came back with our top 10 most connected superheroes. The first result was Captain America, just like we found before. And the way to interpret this is the vertex ID, and what we're getting back is the total number of connections followed by the character name here. So this is the actual degrees result here, the number of edges pointing to that vertex. And number 2 turns out to be Spider-Man, followed by Iron Man, The Thing, Wolverine, so on and so forth. All the people you'd expect, although a little surprised to see Scarlet Witch showing up there. I never heard of her before. Maybe there's a good chance we'll see a new Marvel superhero movie about that person at some point. And then we ran the Pregel algorithm to actually execute breadth first search from Spider-Man to everyone in the entire graph and keep track of their distance. So that's kind of cool. And you can see, just kind of skimming through the data, that that whole 6 degrees of separation thing, well, in reality, it's a much lower number than 6. Pretty much everyone is 1 or 2 degrees from Spider-Man, it turns out. If you get into some really obscure people, you can find maybe a 3 if you're lucky. Let's see. I thought I saw a 3 in here. Yeah, Goom. Goom is 3 degrees, so I have no idea who Goom is. Kind of a cool name, though. And some people just aren't connected at all, like Marvel Boy 2 and Fagin. I mean, odds are they're not connected to much of anybody. And just to check our results, we did a filter looking specifically for Adam 3031, and sure enough, that character is 2 degrees from Spider-Man, just like we found before. So hey, it works. That's GraphX in action. So actually did a lot more than we did before with a lot less code. So it's an example of the power of GraphX in analyzing a social graph, and actually using Pregel to do a more complex algorithm where we're iterating through that graph one step at a time. Breadth first search just being one example of what you can do with Pregel. So there you have it, GraphX in action. All right, so that's pretty much some of the most complicated stuff you can do with Spark there. We've walked through it all, and we've done some examples here. As usual, I encourage you to fiddle with this if you wish. Print out the results in a different way. Maybe sort this breadth first search results to actually see who the most and least connected people are to Spider-Man and print them out in order. That might be a fun little thing to try out. But otherwise, hey, you've made it. That's Spark and all of its associated technologies for you. So let's move on and talk about how to learn more if you're so inclined.